Okay, so now that we have the handshake down, let's think about some properties of the handshake. One property is that both sides derive a secret key that they can use to communicate. So because of the process where we take the Wi-Fi password, derive the blue key, and then that blue key is then used to derive this key in purple, it means that this purple key, somewhere in it, has the Wi-Fi password as one of its components. What this also means is that someone with the Wi-Fi password is able to generate the purple key and complete the communication, and someone without the purple key is not able to complete the exchange and generate the communication. Sorry, that was kind of messy. Someone with the Wi-Fi password is able to generate this key in purple and complete the handshake. Someone without the Wi-Fi password is not able to generate this purple key, and their handshake will fail. To see why, if we look at this diagram again, suppose that someone, like the client, had the wrong Wi-Fi password, well then they would get a wrong value for this blue key, and then at this step they would get the wrong value of the purple key. So once they exchange MACs, one side will be computing the MAC using the correct purple key, the other side will be using the incorrect purple key, and this will cause the keys to be different, and that's a problem, and the handshake will not complete. So that's how we make sure that someone without the Wi-Fi password is not able to join the network, while someone with the Wi-Fi password is able to complete the handshake and join the network. So that's why we've done this sequence of derivations, is to make sure that people with the Wi-Fi password can connect, people with the Wi-Fi password cannot. Now, one other thing that we threw into the deterministic hash soup during this handshake is the nonce and the MAC address. Now, these two values ensure that each handshake that we do is different, because these nonces will be different, and if we do a handshake with a different client, their MAC address will also be different. So what's good about these being different is that every single handshake derives a different purple key. So if you connect to a Wi-Fi network, the key that you share with the access point is different. And if I connect to that same Wi-Fi network and the same access point, the key that I derive will actually be different from yours, because my handshake will have different nonces and my MAC address is different from yours. So this makes it so that every client has a different purple key that they use to send data to the access point, and then the access point can forward that data to the rest of the internet. So that's the consequence of the way we've generated this PTK in purple. Every user has a different one, and that's because of the nonces. So if we want to send data to the internet, we encrypt the data with our purple key, send it to the access point. They can decrypt it and then forward it to the rest of the internet as they wish. Now, one thing that this breaks is the need to broadcast packets. So sometimes, like we saw in ARP and DHCP, you do want to broadcast the message to the entire local network so that everybody can see. But if everyone has a different purple key, there is no way to broadcast the message to everyone, because we're all using different keys to encrypt and decrypt messages. That's where this green group key comes in play. At the end of the handshake, the access point encrypts and gives the same group key in green to every client that connects. So this way, if you want to encrypt messages and broadcast them to the entire group, you can do so using this GTK, and everyone uses the same key to decrypt. That's how you get broadcast messages to work under this encryption scheme.